Good morning, everyone. So today we will discuss send control technology together. And currently, where we meet a bigger challenge for send control. So there are some higher production rates failed due to high send production with BSW increase. So we have to look for a better send control technology to recover this waste production. So today we will introduce some send control method, and we will choose which one is better for us. So for send control information content include what issues of higher sand production, and what cause sand production, and current there are some sand control some sand control technology for advantage and disadvantage for their sand control technology. So first, we will introduce consequences of sand production. So the production of formation sand into a well is one of the problems in the oil and gas industry. Not only does formation sand plug wells, but it also can erode equipment and sit in surface vessels. A company with spends millions of dollars each year to prevent the production of formation sand and to deal with other sand-related problems. So there are some issues of sand production. The first is wearable fail. So if the well have higher sand production, the sands will create sand pressure in tubing or in casing and plug the well. The first issue is equipment problem due to sand fail. So like wearable fail, the sands will create sand pressure to plug tubing and cost shut down this well. The third issue is sand erosion of downhole equipment. So and caused tubing and casing broken and damaged. The fourth issue is sand accumulation on surface. The fifth is erosion of surface equipment. We can find the picture, right picture. The surface equipment will be damaged and broken by sand with higher velocity. The sixth issue is production loss. Yes, of course. When sand bridge plug in tubing or casing or in surface, so we will lose flow rate on surface and we will lose production. Another issues is casing and lining collapse. Like we just talk about. So since we cause tubing and casing broken and collapse. Another issue is the sand disposal. if we get a lot of sand on surface, we should dispose this sand. We will spend a lot of money. Another issue is the environment concerns. So if we cannot deal wells depose this well, deal with and depose this sand well, so we will cause the environment issues. The last issue is sand can cause the facility downtime. So in surface on surface facility, if there are some sand in on surface facility, they cause the equipment shut down and first and facility downtime. So what cause of sand production? So when fluids are produced from sandstone reservoirs, stresses are imposed on the sand grains that tend to move them into the weber along with the produced fluids. These stresses are caused by pressure difference in the formation, fluid frictional forces, and the weight of the overburden. When the combined magnitude of this stress exceeds the strength of the formation, sand will be produced. So below there are some causes of sand productions. The first is totally of weak unconsolidated formation. So it's this main reason for sand production. So if clay containing cement material is not good, so it's easy to cause sand production. Another is viscosity of fluid in place. So higher viscosity will cause sand production. So another cause is improper well completion, like acid stimulation. If we conduct acid stimulation, the one acid will dissolve some clay and cause the sands unconsolidate and cause the sand production. Another is completion fluids or weaker cement also can cause sand production. Another cause is changing stresses in the near weber area. The first is higher production rates. If this well have higher production rates, see the flow velocity is higher, it's easy to cause sand production. Also, depletion of the pressure, where it's easy cause sand production. Another is production of higher viscosity fluids. So water will cause sand production. So water can dissolve the cementing materials, holding the sand grains together, and water increased dragger forces due to increased total fluid rates. Also, water increased drag forces due to two-phase fluid flow. These two water disturb the trucial forces holding the grains together, and disturb the capillary forces holding the grains together. So for our three higher production ways, uh, when they when PSW increase, so cost center production increased also, and we should decrease when we decrease frequency and to decrease flow rate, but center production cannot decrease. So finally, cost this was shut down. We have to conduct a workover to recover the production, and we will pay a lot of money for them. So for sound control method, several techniques can be used to combat sound problems, and they can be grouped into four general categories. The first is production practice. Another is completion practice. The third is mechanical retention. The last is chemical consolidation. So each of these methods, used singly or in combination, has been used to elevate and/or control sound production problems. However, no one technique can be used to control sound effectively under all circumstances. Thus, it is important that the advantages and the limitations of each technique be recognized so that the best produced can be followed. Okay, about production practice. Sound production is the natural consequence of the flow of fluid into a well. Therefore, reducing the production rate will normally diminish sound production as well. The flow of mutation sound into a well is proportional to the velocity, viscosity, product, which is related to the drag force created by the flowing fluid. Laboratory and field tests have shown that sound production can be reduced by lowering the production rate, drag force, to the point that the natural choosing force within the sound hold it in place. Sound control therefore becomes possible through a step-by-step reduction in the production rate, a level at which the sound cut is acceptable. If the flow rate is sufficiently high, no further sound control may be necessary. So there are several factors to affect sound production. The depletion in induced stress and phase changes and pure fluid chemistry and pure pressure and temperature also can impact sound production. Normally, when we manage wells, we are always wanted to increase production flow rate by increased frequency. So this normally operation. But if the reservoir is unconsolidated, if we increase flow rate, it's easy to cost sand production, because if we change the flow rate, there are some pressure change we affect to reservoir and cause some sands remove from the rock and flow into the weber with flow rate and cause the sand production. Another is completion practice. If a well is to be completed in an unconsolidated formation without a sand control treatment, several completion practices should be followed to minimize the possibility of formation failure and subsequent loss of production. In general, these practices are intended to reduce the stress caused per unit of production by enhancing the ability of the formation to produce fluid. They include the use of clean completion fluids, higher perforation densities, perforation of long intervals, and perforation of clean sands. Fluids that are free of solids and compatible with formation material are essential to successful sand control. Partly plugged perforations and all formation damage caused by incompatible or solid-laden wearable fluid can require excessive pressure drawdowns in order to produce desired fluid returns. So for this full practice, the third perforation of long intervals and a waitress perforation technology it's usually used on site. Another practice is mechanical retention. One obvious method of preventing formation sand from being produced is to physically restrain its entry into the wearable flow stream. The particles tend to pressure across such opening, thereby preventing further particle movement. If the size of the particle varies, retention of the larger particles causes the smaller particles to pressure behind them. So, as below figure, with yellow and blue marked in yellow, marked in green and blue. This way, we should use or install tools below tubing or above casing, and to prevent the sands into artificial lifting system and cost and as an system failed. So like a slotted line screen. But if we choose this technology, it's easy to plug by sense, so and cost productivity decrease and affect production. So marked in red, it's a gram pack technology. It's it's better than use screen and slotted liner because this technology has a higher productivity. There are small effect for production layer. So currently it's better technology uh, and broader use in oil field. So all methods of mechanical retention are based upon the principle of retaining a center portion of the formation material to prevent the risk of it from entering the well. Devices used by themselves to restrict sand movement are usually referred to as screen or slot liners. The placement of larger clean sand, actually referred to as gravel because it's much larger than formation sand, between the screen device, the formation is referred to as gravel packing. Another sand control technology is chemical consolidation. Chemical consolidation has primarily involved the use of plastics as artificially cement the formation sand grains together so that the formation fluids can be produced sand-free. To be effective, the practice must weight the sand surface and adhere to the sand grains, yield a higher compressive strength upon curing, and maintain a higher well productivity. Another chemical sand control method involves a resin coated sand, which is mixed at the surface and pumped into the well. The ground plastic slurry is then allowed to settle and cure. After curing, the residue is drilled out of the well, which is then placed on production. Below figure shows the two chemical consolidation method. The first one is about plastic consolidation. The second is about resin coated sand. So, okay, currently we will introduce compilation methods. The first is line and screen compilation. A screen or slotted liner can be simply run into position, and the produced sands allowed to bridge around each. Since low-bank setting or pump-in treatments are normally used, the finer particles are lodged removed effectively from the near Weibo sand mass, and low productivity is usually the result. Completion in which only a screen or slotted line is run in a well have been unsuccessful in controlling sand or maintaining a well's productivity for long period of time. Probably the reason this technique is less successful in oil and gas wells than in water wells is that most hydrocarbon-bearing rock formation are more consolidated than are shallow aquifers. The linear only completion typically decreases in productivity with time because of plugging around the screen slow openings. For this reason, the technique is not preferred. So, so maybe initially to control beginning of the beginning of all of send control, we always use line other screen complex due to no cost. But if this fluid is a higher viscosity, it's easier to plug a line at the screen and cause the productivity decrease, and we will lose production. So e- even we can or the we will lose production completely. We should pull out line and screen so we can recover the production. So currently we we do not use line and screen completion no more. Another completion is open hole garage packs. Garage packing is the recommended method for mechanical control formation and production in oil and gas wells. Like we just talked about, so currently we do not use slot and screen no more due to they will cause no productivity. So the ground packs is a good technology for these wells. This technique as noted early entails using accurately sized gram to exclude formation sand. A screen or slot line returns the gram but allows the entry of fluid into the well. Open hole grab packs are completion in which there is no perforated casing between the grab pack and the screen or slotted line. This completion has the highest productivity of all grab pack completions as far as well completions in general are concerned. Its productivity is surpassed only by an open-hole completion. Below figures shows three types of graph packs. The first one is about open-hole graph pack. The third one is cased-hole graph pack. Use pre-packed. We will discuss pre-pack. What is the pre-pack later? The third is cased-hole pre-pack. Pre-coated pancake. So about open-hole graph packs, the primary disadvantage of the open-hole graph pack is the inability to isolate extraneous fluids, such as gas or water, at the sand face. A second limitation is that not all sand formations are physically structured to accommodate this type of completion because of hole instability. In this case, the sand formations are usually cased off prior to completion. Other than these two limitations, the open-hole graph pack is the preferred mechanical sand control technique when there is no contraindication to its use. As a general statement, it is used greatest effectiveness in long-life completions, in which the production of water or gas will not present a problem. The cased hole graph pack consists of a screen or slotted liner that is graph packed inside a perforated casing. This completion is the most widely used graph pack today in oil and gas wells. It is chosen primarily because, upon the initial completion, it is not always certain if wells will produce formation sand. Consequently, many wells are perforated and then produced. If low sand appearance, a graph pack is not necessary. But a cased hole graph pack can be performed later if sand control becomes necessary. Furthermore, this completion is better updated to exclude water or gas if the need arises. So for open-hole graph pack, used a lot of wells onshore, because for onshore wells the workover cost is very high. So normally for onshore wells will conduct open-hole graph pack initial when the well drilled and completion beginning. They always use open-hole graph pack, so they can decrease workover frequency and with severe cost. For open-hole graph pack disadvantage, for cased hole graph pack disadvantage are: the first, they are not as well suited as the open-hole packs for higher flow rate. Second, They are much more difficult to perform correctly. Both of their limitations arise from the greatly limited cross-sectional area of flow in the sand field perforation of cased hole pancakes compared with that of the open hole. It is therefore extremely important that all perforations, as well as the region outside them, contain gravel of the highest permeability, able to control formation sand production effectively. To perform cased hole panking properly requires that all perforations be open and free of formation sand. When the well is completed, if at all possible, the region outside the perforation should be pre-packed with gram, that is, filled with gram of the highest permeability able to control sand production. The procedure usually includes washing or searching the perforation to ensure that they are open to accept the ground. So we will introduce detailed information later about open hole grab pank procedure. Below below figure shows some different slotted. The first one is vertical gun slotted. The second is vertical slotted. The third is horizontal slotted. For ground pank screen, the liners are much less expensive than their wire-wrapped screens, but they are not as effective. Their use is confined to the situation in which wire-wrapped screen cannot be used economically. In wire-wrapped screen, the wire is wrapped directly on the pipe base, which may be drilled, slotted and glued. Longitudinal rods are also used between the screen and pipe in some cases. The screen slot openings are controlled by nuggets, which are clamped into the rod during screen fabrication. After the wire is wrapped on the pipe base, it is welded at each end of the screen joint and is held in place by two longitudinal welds that extend the length of the screen. Below figure shows a different wire-wrapped screen. Grab pank screen root bases screens are similar to the jacketters on all welded construction screens, but they contain no pipe base. In the manufacture, the wire is resistance welded to longitudinal rods. The final step in the construction is to weld collection on the ends of each screen. While rapid and all-weighted screens have the advantages of offer much more open area per line foot than slot lines. Consequently, they are less susceptible to plugging. They are used in most completions instead of slot liners if the additional cost can be justified. The Y on all-weighted, Y-rapid, and road-based screen is keen-store in shape, that is, it tapers toward the center. The design avoids the liability of plugging as the particulates pass through the screen slots. Tests were made of the wine screen available to the industry in order to determine the strength and flow characteristics. The result of study were compared with the result of the same test performed with a slotted pipe. About graphic screen, tensile strings. Pipe-based screens are about twice as strong as road-based screen under tensile loading conditions. About collapse strength. Collapse thickness of all-weighted screen is related primarily to the excessive standoff of the screen from the pipe base. To avoid no-collapse resistance, close tolerances should be observed by manufacturers. About flow capacity. The flow capacity of screen, slotted liners, and graphics does not pose a significant restriction to flow unless they become plugged. Road-based screens offer no significant advantage over pipe-based screens in flow capacity. The basic problem is how to control formation send without an excessive reduction in well productivity. To achieve effective control implies a good graphic design, the essential elements of which include analysis of formation, grain size distribution, selection of optimal gram size in relation to formation sand size in order to control formation sand moment, use of optimal screen slot widths to return the gram to the gram. So let's take a rest and for 10 minutes and then we'll come back to continue. Thanks.